Hello and welcome to the second part of an introduction to quantum physics. I'm Carl Givella, and I'll be taking you through this infinite square potential example. Okay, now to begin this example, we'll have to define some potential. And we're going to say that at some region, it'll be 0. So that's from this region, 0 to some distance L. Outside this region, so to the left, so that's when x is less than 0, and when x is larger than L, so that's to the right of L, the potential will be infinitely large. Okay, now let's choose a different color. I'll use bleh. Yes. Okay, so here is axis, so it's an x-axis, and this measures potential. Now we said that one wall is at 0, so that goes up there to the infinite, and one's at L, so that's 0 and L. Okay. Now what we'll have to do from here is we'll have to remember from our previous example, in part 1, we defined K equals 2m on h bar squared, and in here it's E minus Vx. Yes. So what we'll do first is we'll look at how the wave function behaves outside, so in this region here. So we know that the potential V of x is infinite, so we plug that straight into there. So we have an infinite, negative infinity here underneath a square root sign, and all these other terms are always positive, so what this will lead to is I infinity. Now also from part 1 we'll remember that we had our time independent wave function, which in general looked like this. Yes, magic. Now we can plug in what k equals here, so out of the way, I infinity x and I infinity x. Okay, so irrespective of what x equals in these regions, this will always be a negative infinity, and this will always be a positive infinity. Right? So this term will tend towards 0, this exponential. The other one will tend towards infinity, which is not good because this needs to be square integral. So therefore b equals 0. So to explicitly describe what we have here, our wave function in these regions is 0. I'll use a different color, gran. So I'll just draw it here. It's 0. There we go. Okay. Now we'll look inside. Let's see how a particle behaves inside. How can we describe it mathematically? I'll get this out of the way. Right. So we know that the potential is 0 here. So we can change this, and it will look something magical. Gosh. We'll get something like this. Now I'll just do a quick side note here. So this equals square root of 2me on h bar. Now this may look familiar to you, and the way we can go about this to find out what this may actually mean is we know that there is no potential in here. So all the energy is kinetic energy. So the particle can be described by this formula here. Now remembering that this is currently non-relativistic quantum physics, so we're looking at only the classical interpretation of kinetic energy and potential. Right. Now also another useful equation is this. So from here, we can almost substitute that directly in. So here, that equals half mv. That's all squared on m. If we square both sides of this, we can put it directly in. So that gives us half a momentum squared, or rho squared, on m. Now we can rearrange this to find something similar to this. So rho equals square root of 2me. Oh, what do you know? So then this equals rho on h bar. That's a very important equation. It helps describe the dispersion of a wave in quantum physics. Anyway, that's not important at the moment. Something a little bit more important at this moment in time would be describing what the energy levels are. So we'll make E the subject, which equals k squared h bar squared on 2m. That's an m. Yash. Righty. Now let's have a look what it looks like, what the wave function looks like inside. So what we can do is we'll look at the boundary conditions that may help describe what the wave function looks like. So we know that the wave function at 0 equals the wave function at L, which equals 0, as you can see. Right? Okay. So the first step will be, we'll say 0 equals AEIKX plus, no, sorry, that should be a 0 plus BE minus IK 0. Exponential to the power of 0 equals 1 for both of them. So that equals A plus B. I'm going to rearrange this so that B equals minus A. Now we'll look at the other boundary. Don't need to draw that. Just say 0 equals AEIKL. And now I'll substitute in what B equals here. So it's minus A e to the minus IKL. Now if you remember from Euler's formula, yes, we can do this magic. Oh yeah, fantastic. And see these constants? Let's put them all into one constant. Much nicer. Oh yes. Now, we have this equals 0. That can equal 0 when A prime equals 0. But that's trivial. That doesn't actually describe anything for us. The particle may as well not be in the potential well. So we have to see how this sine function can equal 0. And that occurs when KL equals n pi for all integers from 1, so on. Righto. I'm just going to rearrange that equation so we have k equals n pi on L. Right. So we'll say wave function outside, well, we now know that it equals 0. And inside the well, inside this region, x equals n pi x on L. And now we also know, well, I'll do it up here, we know what k equals. K equals n squared pi squared on L, L squared down there. All this. There we go. Alright, so now for this to be of any use to us, we have to normalize this wave function. A wave function must be normalizable for any information to be measured from it. So we have to normalize. Righto. So how do we normalize? So say normalizing is equal to 1. Normalize the wave function. I'll write everything out explicitly here. So this norm squared equals the integral from negative infinity to infinity of the complex conjugate of our wave function times the wave function. and since this is in only the x direction, that's dx. If it was all space in all directions, that would be, would write it something like, I don't know, tau. Anyway, to represent all, or maybe the r vector. Anyway, so we'll substitute in what our wave function is. So we have a prime, complex conjugate of sine, complex conjugate of that, and by x on L. Then a prime, sine, and by x on L again, dx. Now, it's not actually from, it is actually from the negative infinity to infinity, but doing this piecewise, we'll find out that anything here, the integral will return 0, and anything here, the integral will return 0. So piecewise, we are only looking at in here. So by addition of all the integral parts, we only have to go here, 0 to L. Right. Now, something interesting here. The complex conjugate of this, you think, oh, well, there was a 2i in there, so the i should go negative. Well, the a originally was possibly already complex, so we can't actually tell if it's going to go become a negative a prime. So we have to leave it as an ordinary constant. So say the complex conjugate of 2 equals 2. Right? Let's continue. So we'll simplify this. Get a prime outside, take that constant out of the integral. 0 to L, sine squared. Oh yeah, we have to say how that works. N pi x on L dx. So just a quick note on complex conjugate of sine. Actually, I'll write it first, like this. That equals this by Euler's formula, one of the derivations of it. Right, and if we do this complex conjugate, we get a negative I here, negative I there, and a positive. This negative can go inside here, so I get that, and so all you get in return is sine theta again. That was just a quick aside on that too. Right, anyway, let's do this integral. Yeah. Wow, let's simplify it. Let's simplify this. Nice trig identity helping us out. There we go, much simpler to do. It's another work. Bracket. Okay, now we know how to do this. This is really simple to do. So that's a prime squared on 2 x minus thingo and stuff and other things. 0 to L. Right. Now, this L will go into here, and we get an L. When we put the L into here, the L's will cancel, and we get sine 2n pi. Now, if we remember unit circle, so we start off when n equals 1, so it's gone round once, so sine is 0, that's 2 pi. So we go n equals 2, go around again, 4 pi, sine is 0, and so for all n, sine is 0, so that term will also disappear, and of course 0 and 0 there, 0. So in the end, this integral evaluates to a prime squared on 2 times L. That's really cool. I'll clear this. My giant duster for my blackboard. Yes. Alright, so what we found is that a prime equals 2 on L. And from that, we can say what our wave function equals inside the potential. So it equals that. That's fantastic. It's a sine wave. So the first term, wave function for n equals 1 looks something like this. It's we look at the sine wave like that. It's this part here. There. And we look at n equals 2. It will be to this point here. So like this. And n equals 3 is to that point there. So and so on, like that. It's fantastic. Well, there you go. That's how you go about, at least from 0 to L, for the infinite square potential. Hope you enjoyed it. I certainly did.